In part 5, we looked at the use of area reduction factors to find an average value of a design rainfall for a large catchment. In this presentation, we're going to be looking at the temporal patterns of design rainfalls. Okay, so let's consider a design rainfall that has a 24-hour duration and happens once every 5 years. Okay? And it's located in the east coast of Australia. How does it actually fall over this 24-hour period? So 24 hours of rainfall is quite a long time. Do you think the rainfall will fall at a constant intensity over this period, or it will have some variations? So from our experience, we know that the rainfall intensity will vary over time in this 24-hour duration. So it is unlikely that the rainfall will be like this one represented in this graph, which shows a constant intensity rainfall. So a constant temporal pattern is unrealistic, but sometimes it is okay to assume if we are dealing with a small catchment and for short duration. So think about 24-hour period. We will have more variation of rainfall intensities during that time period as compared to a short duration rainfall, such as 30 minutes. Okay? All right, so here are some common temporal patterns for a rainfall event of 24-hour duration and a average recurrence interval of 5 years in the east coast region of Australia. So as we can see, the rainfall distributed over 24 hours has various intensities. For some of them, for example, this example here has the largest intensity is in the beginning of the rainfall event. Some others, let's have a look at this one, for example, has the largest intensity happening in the center of the event. Some others are a bit more uniform, for example, this one, which approximates to a constant intensity. Okay. Now, each one of these temporal distributions will generate a different outcome in the catchment, a different hydrograph. As we can imagine, if we have a constant rainfall intensity, the response of the catchment at the outlet will probably be a flatter hydrograph. But if we have a rainfall event with a peak rainfall concentrated in a short period, you probably will have a hydrograph with a peak flow, with a higher peak flow than if we had a uniformly distributed rainfall event. So the Australian rainfall and runoff have specified 12 temporal pattern regions for Australia. So here we have the list of the regions as well as here, and a map showing these regions. Okay. For each region, observed rainfall data has been analyzed and 10 temporal patterns have been created for 3 AEP groups. Okay, rare design rainfalls, intermediate and frequent design rainfalls, and using 18 rainfall durations ranging from 15 minutes, actually this is incorrect, it's actually from 10 minutes to 10,080 minutes, okay, which is 7 days. So here is the definition of the rare, intermediate, and frequent rainfall events. The rare ones would be rarer than 3.2% AEP, intermediate events between 3.2% and 14.4 AEP, percentage AEP, and frequent events would be the ones more frequent than 14.4% AEP. This is an example of the 10 rainfall patterns for the Southern Slopes region for 120-hour duration rainfall events. Okay, so we have intervals, 40 intervals in which each interval is 180 minutes. So the total is 7,200 minutes, which is equal to 120 hours. And this is how the patterns have been developed. And remember that these patterns, they are not random patterns, they are patterns that actually exist, they actually have the same probability of occurrence. So we have 10 rainfall patterns of same probability of occurring for that duration rainfall, okay? All right, so temporal patterns of design rainfalls. We can download these temporal patterns for each of those regions that we just saw in the previous slides. We can download them from the Australian Rainfall and Runoff Data Hub, which can be accessed through this link. You will need to enter the longitude and latitude of the location that you are interested in. You have to click on temporal patterns because we've got different hydrologic variables to be downloaded here. And now in this situation, we are interested in temporal patterns. And then click submit. This will create a zip folder, which we will have to download, unzip, and then open the following file, region_increments.csv. Now I'll just open up here one of those CSV files for one specific region in Australia. And as I said, we have different AEP classes. We have 3 different classes: frequent, intermediate, and rare. For each of them, we have different durations. So we start with 10 minutes, then we follow by 15 minutes, and then 20 minutes. And this is how the rainfall is distributed over time during 10 minutes. The time step is 5 minutes, and we have 58.06% of rainfall falling in the first 5 minutes, and 41.9% of rainfall falling in the second 5-minute interval. So we have always 2 values here for this first example, because we are talking about a rainfall duration of 10 minutes and the time interval is 5 minutes. So that's why we've got 2 increments. Okay, so and these are the 10 patterns. Each of these colors represent the 10 patterns of rainfall. We can see here that we start having 3 increments, because here we are talking about a 15-minute duration and the interval is still 5 minutes. Okay, so for 15 minutes we have 3 increments. For 20 minutes we will have 4 increments. Okay, for 25 minutes we will have 5 increments with the distribution, percentage distribution. The sum of the numbers in each row should add up to 100, okay, because it's 100%. Now, when and how should one use rainfall temporal patterns? I think it's better to explain this question by showing you this example. So let's consider this a creek, which is located in the Northern Territory, and the catchment of this creek is 72.3 square kilometers. The coordinates of the centroid of the catchment are these ones. A rainfall runoff model was set up for the catchment. So that means a rainfall runoff model means a model that transforms rainfall into runoff. The model will be used to estimate outlet peak flows for rainfalls with 1% AEP and for the following durations: 1 hour, 2 hours, 3 hours, 4.5, and up to 24 hours. The storm duration that provides the highest discharges will be taken as the critical design storm duration, and the design discharge will be the average discharge from all available patterns related to that duration. Okay, so let me try to explain what you should do here. You will take the design rainfall from BOM for that particular AEP and those durations. Okay. For each of these durations, you have 10 different temporal patterns, as we saw in the previous slide. So you have to go on the Data Hub, download the temporal patterns for that particular region, which is the Northern Territory. Once you have the 10 patterns for each of these durations, see you have 1 hour, 2 hours, 24 hours, each one of these will have 10 patterns. So you run your model for those patterns. So if we have 1, 2, 3, 4, 5, 6, 7, 8, 9, in this case we have 9 rainfall durations. So 9 times 10, we will have 90 different simulations. Here we have the durations that we need to work with, we need to simulate, and this is specified here, okay? All right, so we have this 100 here, as you may remember, refers to 1% AEP. So 1 every 100 years, roughly. Here we have the design rainfall intensity at the centroid of the catchment for 1% AEP. This came from the BOM IDF system. Okay, so far, so good. We know how to do this. Then we need to apply the area reduction factor because that catchment is bigger than 1 square kilometer. Okay, so don't forget to apply reduction factor. So we have a representative value of the design rainfall for that catchment. All right, so here is the ARF, which came from the hydro tools that we mentioned before, and you need to enter the northern coastal region, the area of the catchment, and the AEP, and the rainfall duration. Okay, so those are the inputs for that tool, and the output is the area reduction factor. Then you will calculate an aerial design rainfall, which is the design rainfall times the area reduction factor. And then you use these rainfalls as input in the rainfall runoff model. Okay? Okay, but what about temporal patterns? For each of these rainfalls, you have to use 10 temporal patterns. So you go to the Australian Rainfall and Runoff Data Hub, enter the required location, download the file, which is a zip folder, then look for the rare events because it's a 1% AEP for each rainfall duration. And note that the rainfall durations will have 10 patterns each. Therefore, nine rainfall durations, which are these 9 rainfalls here, times 10 patterns equal to 90 patterns in total to be simulated in your model. Let's use the first rainfall as an example. So let's take this one as an example, the rainfall with 1 hour duration. Yeah. So here is the CSV file that I downloaded from the Australian Rainfall and Runoff Data Hub. I'm looking at the 60-minute duration and a rare event. And this is how the rainfall is distributed over time. The time increment is still 5 minutes. That's why I've got so many points here. And we can see that some of the patterns have a majority of rainfall in the first interval. For example, this one, the third pattern is one that has 29% of the rainfall falling within the first time interval. So we've got different patterns, and this is what they look like. This is the distribution of rainfall over time in percentage terms. Okay. And I will use these patterns as input in my rainfall runoff model. Okay. So the model results will be the peak flow for each of these simulations. So let's assume that these discharges here are the peak discharge for each of the patterns. Okay. I have just emphasized here the one that generated the highest peak, which, as you can see, came from a rainfall event that is mostly concentrated in the first time interval of its duration. Okay, and we also have the one with the lowest peak, which is one that has one of the most uniform distribution of rainfall. Okay? Now, this procedure needs to be repeated for all the other rainfall durations. Okay? The simulation of 10 rainfall patterns. Then it's customary to plot the discharges on the y-axis against the design rainfall durations. Now here is a box and whiskers plot, which represents the simulation, the results of the simulations from the 10 rainfall patterns. Okay, so each of these represents 10 simulations. The lowest value of the box and whiskers plot, the lowest, horizontal line represents the lowest value of our peak discharges. If we go back to the results here, this will be the 141.6 cubic meters per second. So that's the this value here at the bottom. And remember that this first box plot is only for the first rainfall duration. The other ones are for the other 8 rainfall durations. The lower, the bottom of the box represents the first quartile of the results. The middle line represents the median. That star represents the average of the 10 rainfall pattern simulations. The top of the box represents the third quartile, and the top of the whiskers represents the maximum value, which is that 179.6 cubic meters per second, which is this one. The result that came from the simulation of this rainfall event. Okay, so it's a lot of work that you have to do when you have to find a proper design flood. As you can see, you have to simulate different durations and then find the one that leads to the maximum discharge. In this case, the design rainfall will be this one. Okay, why is that? That's because in this case, if you look at this question here, the storm duration that provides the highest discharges will be taken as the critical design storm duration, and the design discharge will be the average discharge from all available patterns related to that duration. So the critical duration for this catchment is 180 minutes, and the average discharge is the one represented by that star here. So the average peak flow of all 10 patterns related to the 180 minute duration rainfall should be taken as the 1% AEP design flow. Okay, so this is the general procedure to find the design flood. Now, what we'll be looking at next is how to transform the rainfall event into runoff. We'll be looking at some methods to generate that design flood using design rainfall as input.